In the first volume of LightWave lessons, we learned about LightWave. We learned some of the specific features of LightWave and Modeler. We learned how to create a television commercial, and in the references section, we learned certain settings to achieve specific results. Now LightWave has been out for over a year, and most of you are feeling comfortable with its user interface and features. So in this, the second lesson, we're going to take a different route. Instead of telling you about certain features of LightWave, we're going to help you understand LightWave. Take ripples, for example. In the last tape, we gave you exact settings to use. Now, this was fine for a starting point, or if you wanted to achieve the exact result that we had on screen. However, in this tape, we're going to help you understand the ripples and the settings. When you are finished, you should know enough about ripples to get any effect you want from them. Now, we're going to cover several sections of LightWave in this manner. Let's understand transparency. Now, we've all played with the transparency slider, but have you experimented with the other options under transparency? Let's look at them now. Under transparency and texture, we have planar image map, cylindrical image map, spherical image map, checkerboard, grid, dots, marble, wood, and fractal noise. You see, the slider is not the only way to set the transparency level. You can also use a picture to tell LightWave where the transparent areas are. Now, LightWave does this by looking at the picture in a special way. The brightest areas of the picture are the most transparent. The darker image are more opaque. Let's look at some examples done with some of these special options. I've created a gradient picture in Deluxe Paint. Using this as a transparency planar image map, we see a good example of the way LightWave interprets a picture to set transparency levels. Here's our gradient picture, painted in Deluxe Paint, and set as a planar image map in transparency. Now we'll put a pencil object behind this and turn the planar image map on, and you can see how LightWave interprets the picture. Brightest areas become transparent, darker areas stay opaque. As you can see, some effects that would be difficult to achieve otherwise are easier thanks to transparency mapping. Let's go through a brief example of exactly how to use this feature. For this first example, we're going to use transparency mapping to put two-dimensional objects in our 3D scenes. Here we have a picture of a lady that was done in Deluxe Paint. If we wanted to put this into a 3D scene, we'd use texture mapping under transparency to get rid of the background. The effect looks like this. Now let's look at the settings needed to achieve this effect. Under Deluxe Paint, we have our picture rendered. Now we need one more picture, and that's going to look like this. We have black everywhere the girl's picture is, and white everywhere the girl's picture isn't. You see, the theory behind this is, wherever LightWave sees white, it'll make it transparent. Once I've saved my images from Deluxe Paint, I get back into LightWave and set my surfaces. In this case, we're dealing with a surface called Picture. The first thing I do is map the picture of the lady onto the surface. I go to Surface Color, Texture, a Planar Image Map, and the texture image is 2D Map. That's the name I've given to the picture of the lady. Texture size has been set to 5 meters by 4 meters, the size of my object. Now I do the same thing under transparency. Under texture, planar image map. This time I have 2D transmap, which is the name of the black and white image of the lady. Everything else is the same, z-axis and texture size. Now what it'll do is it'll apply that same map to the object, and again, wherever there's white, it'll be transparent. Wherever there's black, it'll be opaque. Let's look at it again. Here's what our image looks like before transparency image map is applied, and here's what it's like after. Now this is an excellent way to put trees and cars and people in your background of your 3D scenes. Things that are normally very hard to model in 3D that you can paint easily in Deluxe Paint or any other paint program. Get rid of the edges with transparency map and pop them right into your 3D scenes. Let's look at another reason to use transparency mapping. Here we have a picture of the world. Nothing fancy here too much. We did use image mapping, spherical image mapping, with a picture that we've done in Deluxe Paint of the surface of the world, but by using that same surface map in black and white this time and using under transparency map, we get this effect, a really neat effect. And let's look how we did this. In Deluxe Paint once more, we draw our image, this time a picture of a flat world. Here in green and blue, the colors that we really want to render in our scene. Next, we adjust the palette. We're going to make everything blue, in this case the water, white. And we're going to make everything green, the landmass, black. And we save this under a different name. Once we've saved our images again under Deluxe Paint, we pop back into LightWave. Here's our simple scene, just a picture of a simple sphere. Now we need to set our surfaces to it. This time we have a surface of Earth. The first thing we do is under Surface Color, Texture. We're using Spherical Image Map now, because it's round. We pop in World Map Color, the name of the image drawn using the blue and green colors. Under Transparency, we do the same thing, Spherical Image Map, except this time use World Map White Sea. Apply the texture and render it out. Here's our final rendering. As you can see, it's applied the green-blue map to the sphere, and when we render it with that transparency texture mapping on, it renders the sea invisible. Now, one quick note, you see how you can see the continents through the other side of the globe? That's because our sphere was two-sided. When we created in Modeler, we had it two-sided. That's important when you're doing transparent things. By the way, if we would have used gray in Deluxe Paint instead of white, our sea would have appeared sort of transparent. The brighter the image, the more transparent. Using transparency in conjunction with soft edges is a great way to achieve a glowing light effect. Now, this can be used for spotlights or for achieving an atmosphere around a planet. Let's understand how to use this effect. You may remember this picture from our title page. See the large planet? A slight blue-green glow around it? That's our atmosphere. Let's zoom in a little bit closer. Now you get a better example of what we're talking about. This is a transparent soft edge sphere around another sphere. Let's take a look at how we did this. Let's take a quick look at our object under Scene Layout. You see it's two spheres, one large sphere around one smaller sphere. Of course, our larger sphere is the atmosphere. It's going to be transparent with soft-edged mapping. Also, our atmosphere sphere is two-sided. Remember that with your transparent objects. If we page through surfaces, you can see we have planet, atmosphere, those two surfaces. Let's go ahead and set those. If we go to planet, it's a simple spherical image map of something we have called Saturn IFF. Smoothing, of course, has been turned on. If we go to atmosphere, luminous has been turned on to give it a brighter look. Color highlights has been turned on. Now it's a blue-green type atmosphere. Color highlights means whatever comes shining through it, even light sources, will appear to be that bluish green. Transparency has been set to 75%. Of course, if we had it very much higher, we wouldn't see it at all. And if we had it too much lower, say under 50%, we wouldn't see the planet surface at all. The atmosphere would be too dense. And under edge opacity, we have clear. Now what this does is it kind of blends and smooths the edges of the atmosphere with the surrounding edge, in this case the blackness of space. So transparency combined with clear edge opacity produce this effect. Let's look at it one more time. And here's our final rendered image. Notice that you can see the edge smeared in with the black space around it. That's that soft edge taking effect. In this picture we have two spheres. The only difference between them is the one on the left is a one-sided object. The one on the right is a two-sided object. Notice the double highlights? The light reflects coming in and going out. This is a definite necessity for glass-type objects. By the way, the transparency slider was set to 50% in this scene. By now you should have a better understanding of transparency and some of the transparency image mapping settings. Now I want to show you some of the neat effects that can be achieved with the remaining options under transparency texture mapping. For instance, the checkerboard pattern. Every other check in the pattern is transparent. The same thing is true with the marble setting under transparency. LightWave interprets part of the marble texture as transparent, while it picks up the color defined in your object color as the other part of the marble pattern. Here's a neat effect. By combining the transparency mapping of the marble texture and also the image mapping under the surface color setting, we can use transparency and image mapping on the same object. Notice you can still see parts of the pencil behind this picture. Now this is the effect that fractal noise transparency mapping has. It doesn't look like a lot here, but this effect can be used for smoke, clouds, and even fire. Let's take a quick look at an example where we use fractal noise transparency mapping to make a cloud scene. For this cloud example, we'll use this city as a backdrop. Now again, using the transparency fractal noise mapping, we will map fractal noise clouds over this city. Here's the effect. Bump mapping can be great fun to play with. However, getting the exact look we want can sometimes be frustrating. It helps to understand all the settings and attributes associated with bump mapping. Did you know that using a picture under bump mapping produces a great embossed picture? This is one feature you need to know. Let's learn how to understand bump mapping, ripples, and fractal bumps. Remember I mentioned embossed looking pictures? Here's an example. We take a simple 24-bit picture of flowers here, and under image mapping, under bump mapping, we can turn them into this great looking embossed effect. Now I hope you can see the detail that it maintains in the image here. Let's look at the technique we use to do this. Under scene layout, we're starting with our simple picture frame again, an object that measures 5 meters across by 4 meters up and down. Under images, I've loaded my image called flowers.iff. Under surfaces, we have our picture surface. The first thing we do under surface color is set a planar image map with flowers as the picture on the z-axis in this case, and with a texture size of 5 by 4. Under bump mapping, we do the same thing. Texture type is planar image map using that same picture as a bump map. The texture image is flowers IFF, z-axis, texture size is 5 by 4. If we look under the layout, we see I have my normal picture object, which measures 5 meters across by 4 meters up and down. Under images, I've loaded up a picture called flowers.iff. Now I go to my surfaces. I have one surface in this case called picture. The first thing I do is set my surface color. Now whatever color I use here will be the color used for the embossed effect. In this case, I'm using a light green color. Under bump map, I go to planar image map, use flowers IFF as my texture image. In this case, I'm using the z-axis to map it on, and I set a texture size to 5 meters across by 4 meters up and down. Z doesn't matter because that's also my axis. I hit Use Texture and Render. Here's our rendered image. Again, that light green colors come up. We get that nice embossed look. Take a look again at the flowers we used to map on there and see how LightWave takes the brightest parts of your picture and brings them up, and the darkest parts of your picture and brings them back. What a great effect for backgrounds. Here's the output of our next example. We're going to do the 3-leaf logo, start it off big. Using texture size, we're going to scrunch it down, add a 3D object, and keep that embossed look for our background like I mentioned. A great effect. Let's take a look at how we did this one. Okay, here's our starting point for the embossed picture we just showed you. In Deluxe Paint again, I've rendered a picture with 4 colors. We're only using 3 in this example, but a medium gray is the background. Bright white is the foreground. Those are the things that are going to appear raised up. And dark black is the text is going to appear pressed in or embossed. So we have that kind of double-edged sword. We have the white coming out, the black being pressed in, and I'm using gray as a medium background so it offsets those things even more. So I go ahead and save this. Here we are in our scene layout. We have, of course, our 3-leaf clover in the center of our 4x5 picture again. Exit the layout, and we'll look at our surfaces. Clover, of course, we have that set to a great green. Diffuse and specular have been slid all the way up, and a glossiness set to low. Now that'll give you kind of a metalish looking effect that's kind of neat. And of course, smoothing has been turned on. We go to our picture now. The embossed part, the background, we've got surface color set to this medium color gray. Under bump map, we have planar image map. The texture image is 3-leaf emboss, plotting on the z-axis. And texture size normally is 5x4. That would give us one big image that we showed you at first. But we want 5 little embossed 3-leaf logos going across and 5 little embossed 3-leaf logos going up and down. So we're going to set the X texture size to 1 and the Y texture size to 0.8. That'll give us a grid of 5x5. We simply divided 5 into the 5x4 numbers. Use texture, and let's render the results. Let's first take a quick look at our 3-leaf logo rendered without the shamrock on top. Remember, this is our deluxe paint picture. The imprinted parts, or the text, is the parts of the deluxe paint picture that were rendered in black. The shamrock part in the middle was the part that was rendered in white. It's raised. That's how LightWave interprets a bump map planar map image, is it puts brighter areas of the image up front and raised. Darker areas of the image are imprinted or pressed. Now let's look at it with our full shamrock rendered on top and our map scaled down in the back. Remember how we got the map parts small in the back? We went under texture image size and we decreased it. We divided it by 5 essentially because we wanted 5 little pictures going across and 5 little pictures up and down. So we have that grid type of embossed effect. Real impressive. Are you keeping up with us so far? Good. Next we're going to look at bump map using the ripples feature. Now this is great, of course, for swimming pools and everything else. We're going to delve into it just briefly so you understand the different settings involved and what they do. Let's take a look at some examples and then we'll go into how we created those. Here's our first example we'd like to talk about, a simple scene, a moon, an island, an ocean. We're going to talk about how we got these ocean waves to look at. Let's take another angle at this, and you can see how we have the ocean waves spread out, and they're not so much in a circular pattern that when you're experimenting with ripples the first time, a lot of times you'll get just that simple one splash effect and circular ripples coming out. This is kind of a more broken up feeling. And we're going to go into how to create this type look, and we're going to go into the settings needed to achieve each one of these specific looks. Okay, here's the main picture we're going to start with. We're going to learn how to do each section individually. Let's take the top left section of the picture. You can see it's a simple wave pattern, like somebody threw one stone in the middle of the water and it's one single source rippling out. Let's look at the settings needed to achieve this effect. Okay, for that top left-hand portion where it looks like one stone was thrown in the water, this is how we did that. Our texture size, here it's set to 0.08 to 0.05. Now, it doesn't mean anything per se except to say that it is the exact size of our object. So if you want this particular look, make your texture size 100% or the exact size as your object. Another thing we did is we set wave sources to 1. Amplitude set to 50. Now, that doesn't matter a whole lot. That's just how high your wave is. 100% would be very high. And by the way, a trick here is you can set amplitude higher than 100%. You can type in 500%. Now, that's not documented, but you can get some strange effects like that. But here, we're going to set it back down to 50. Our wave sources was 1. That's like one stone being thrown in the water. and our wavelength is set to 0.1. That's 0.1 meters, and what that is, that's 0.1 meters between crest to crest of the waves. Now this can vary greatly depending on the size of your object. In other words, if you had an object that was 100 meters by 100 meters and you put 0.1, your waves would be really close together. So you have to watch that. It really depends on your size of your object. Wave speed's just for animation, so it has no effect here in this still rendering. Let's look at it again so you can see how these effects come together and look. For the next section, in the top right-hand quadrant, everything is almost the same. Texture size is 0.08 by 0.05. Again, that's 100% of our object size. Amplitude's the same. Really, the only thing we've changed is wave sources. Now, this is like 3 rocks being thrown in the pond, and it kind of distorts the main wave a little bit. Here's what this looks like when rendered. Again, the top right-hand quadrant. Now, these are the settings for the bottom left portion of the screen. Texture size has been changed. Now it is 10 times greater than our image size. Our texture size is 10 times larger than our object size. In this case, 0.8 by 0.5. Amplitude stayed the same. Wavelength has stayed the same. Wave sources has gone up 1. So now there are 4 stones thrown in the water, creating individual sources of ripples. Let's look how this is created, or how it looks when it's rendered. This is the bottom left quadrant. Finally, we come to the bottom right portion. I think this is the coolest of them all. Texture size now is 100 times the size of our object. So if you're working with an object that's 1 meter by 1 meter, your texture size would be 100 by 100. Okay, amplitude stayed the same. Wave sources has now been increased to 6. There are 6 big stones in the ocean creating wave sources now. Wavelength has stayed the same. What I want you to get out of this is texture size is what really affects it. If you have a texture size 100% of your object, it looks like it does here in the top left-hand portion. Real close, solid circles coming out from one wave source. If you expand your texture size way out and increase the wave sources, it looks like it does here at the bottom right. A whole bunch of individual sources, real broken up water, and that's what we used here in our moon water scene. Finally, let's take a look into fractal bumps. Now, these can be used for everything from grass to putting a weathered appearance to objects. We're going to take the same route as we did with the ripples. We're going to show you a quad screen with different settings, explain how those look, and we'll also put them on an object and show how it's used there. See, the problem with computer images is they're too clean and slick. You never get an apple that looks like this at the store. Fractal bumps can be used to put a weathered or beaten appearance. Now, not necessarily this beaten on a piece of fruit, but on everything from planes of grass to water surfaces or metals to give it that kind of used look and not so clean and plastic. Here's our quad picture that we're going to use with the different bump map settings in there, and we'll explain how we got each one of these, starting with the top left quadrant. Here we are in the fractal bumps area. Our texture size has been set to 0.08, 0.05, and 1. Now this is 100% of our object size again. Our texture size is 100% of our object size. The only thing we're going to change here is the frequency setting. The top left-hand portion will be set to 1, then double to 2, then double to 4, and double to 8. Let's look at the picture and I'll explain. Okay, here we go. Again, texture size is 100% of our object size. In the top left-hand quadrant, we're using a frequency of 1. Next to it, in the top right-hand quadrant, we're using a frequency of 2. At the bottom left-hand quadrant, we're using a frequency of 4. And at the bottom right-hand quadrant, we're using a frequency of 8. 8, of course, gives us very rough appearance. 1, a very smooth appearance. Let's look how this affects an object. Back to our apple again. Under the apple, this is our plain apple. The first example we'll have is a frequency of 1. Very few, very smooth bumps. If we increase our frequency to 5, we get our real distorted apple, real rough appearance. So that's the difference between frequencies of 5 and frequencies of 1. A good surface is most important when rendering a realistic looking object in LightWave. Now, to get a good surface, you're going to have to understand the settings under the textures. Let's look at some of those now. We're going to be looking at texture axis, texture size, texture center, world coordinates, fall off, and velocity. These settings directly control the quality of your texture map, so understanding these settings is paramount to rendering a quality image. Texture axis. This determines which axis or face of your object the image will be mapped on. In this example, the letters have been mapped on different axes. The Y has been mapped on the Y-axis up and down, the Z on the Z-axis front to back, and the X on the X-axis left to right. In this scene we have a simple flat plane. We're going to map an image onto it, and we're going to want to map on the Z-axis because you can see we're going to want the image to go flat on top of the plane. Let's look at the camera view now. We see the Z in the background. We're going to map right onto this. When we render out our image, this is what it looks like. Now let's take a look at what happens if we would have mapped on to an incorrect axis. Let's try the Y-axis and render that and see what happens. Notice that it's a straight pattern. Now what's happened is the cobble pattern started at the top of the image and the very edge of it was pulled down along the front. It was mapped incorrectly. To illustrate the point one more time, let's render on the X-axis. Now what's going to happen is it's going to start from the left to right and pull the pattern over. So we're going to kind of get a left-right pattern. Let's look at it. There it is, the left-right pattern. Usually when you pick the wrong texture axis, you notice immediately because you get a pattern like this. Now let's look at texture size. In our example, we have a plane which measures 1 meter by 1 meter, X and Y. Now it doesn't measure in the Z-axis front to back, it's perfectly thin. Also, we're mapping on the Z-axis. The texture axis is set to Z-axis. So whatever we set in Z under texture size doesn't really matter at all. It just matters for X, which is left to right, and Y, which is up and down in this example. We have our texture size set to 1 and 1, and that's why we saw one big grid on our cobblestone. But if we set the texture size to 0.1 and 0.1 here, what's going to happen is this is 1/10 of a meter. So it's going to take 10 cobblestone patterns to fill the 1 meter grid. Well, let's look at an example. We'll say OK, and we'll render this. Here's our output. Notice a lot finer cobblestone pattern. It's taking 10 cobblestones across the X direction and 10 cobblestones up and down the Y direction to fill the 1 meter plane. Now let's enlarge that pattern a little bit. Let's make it 5 cobblestone patterns across and 5 cobblestone patterns up and down. We do this by going back into texture size, and in this time, instead of 0.1, we'll put 0.2 under X and 0.2 under Y, and render that. Here's what the image looks like when it has 5 cobblestone patterns across and 5 cobblestone patterns up and down. You see how varying the image size varies the final outcome here. Now what would it take to get 2.5 cobblestones across and 2.5 cobblestones up and down? Our texture size is 0.2 meters in the X and 0.2 meters in the Y. And we have 5 cobblestone patterns going across and 5 cobblestone patterns up and down. If we wanted to half that, in other words, have 2.5 cobblestone patterns across and 2.5 cobblestone patterns up and down, we would double our texture size. In other words, we'd put in 0.4 in the X and 0.4 in the Y and render that. I stopped the rendering short here so you can see a good example of before and after. Now before we rendered 5 patterns across by 5 patterns up and down. Our texture size was 0.2. Then we doubled our texture size to 0.4 and we rendered 2.5 patterns across by 2.5 patterns up and down. The top half of the portion is the one with the larger texture map. Now obviously you have to have a pretty good idea of the size of your object before you start doing these measurements. In other words, if you don't know if your object's 2 meters by 2 meters, you won't know the proper texture map size to put on it. Now by the way, what do you think would happen if we adjust our texture size to 2 meters by 2 meters? Remember, our plane is 1 meter square. So if we tell it that our image that we're mapping on it is 2 meters by 2 meters, it's going to double the size of that image and stretch it on there. It's really going to blow up our little brush and kind of pixelize it, but let's look at it and see what happens. Now to double the size, we're going to go into texture size and we're going to change X to 2 and Y to 2. Remember, our plane is 1 meter by 1 meter, but we're telling it that the little brush we're mapping on it is 2 meters large by 2 meters large. We're not even going to see the whole brush when it's through, but let's render it. Wow, take a look at this pattern. We hardly get one brick on the 1 meter plane. But that's what happens because we told it that our brick pattern is twice as large as our object. Okay, I think you get the idea of texture size and how that affects your image mapping onto it. By the way, if you're not sure of the size of your object, you can go into the LightWave modeler, kind of get a rough feel for it there, measure it, come close to it in meters, come back. If you're not sure, make it a little bit larger, your pattern, than the object. Now let's take a look at texture centering and how that affects the image. We're going to look at texture centering. Now I've switched the picture that we're going to map, but I've kept the object the same. It's our 1 meter plane. If I go into texture center, it is set for 0, 0, 0, and that's the default in which you'll usually use. Let's look at the picture as it's rendered now so you get an idea of what it looks like before we mess up the centering. Again, our object's the same. It's the 1 meter square, but I've used a different picture, the 3 Leaf Productions logo, mapped on there, and centering is set to 0. It's exactly centered on the square. Now, if we wanted to shift the picture, the clover, and the text over to the left, let's say, how would we do it? Remember, the x-axis is left to right, the y-axis is up and down. So we're going to tell it to shift the centering a negative number to the x-axis. Let's look at it on the screen. Let's go into texture center and let's shift the image over to the left 1/2 meter. Remember, our object is 1 meter by 1 meter square. X is our left to right coordinates, so we're going to say negative 0.5 for texture center. That means shift it over to the left 1/2 meter. Let's render that. And here's our rendered image. It shifted again 1/2 meter, which is half of our object, a meter, shifted it over to the left, and it's wrapped it around back on the right side. Now you can use this to center wood grain patterns on tables and chairs or whatnot, but use this texture centering and move it around to center your image just right. It's a pretty easy feature to use. Texture centering can be handy for moving wood patterns around so you get the pattern just right on a table or chair, or things of that nature. You won't use it too often, but you can see how to use it here. It's a pretty easy feature. Now let's take a look and try and understand the world coordinates button. It's either on or off. You're either using world coordinates or you're not. Now, world coordinates ignores the settings of the object that were set in Modeler. Now, it's a little confusing, I know, but let's understand this. You take an object from Modeler, it's a meter square like our object. You bring it into the scene layout window and you use one of the options called stretch or size to adjust that object. Now, our object's originally 1 meter square, but if we go into stretch, we can move that object any way around and it's not going to be 1 meter square any longer. Now remember our texture sizing example before. If we have a 1 meter square and we apply a texture map to it and say our texture map is 1 meter square also, then we go into the scene layout and stretch it to where our object is now no longer a meter. It might be 5 meters long. It will still map on just like it were a meter if world coordinates is off. If we click world coordinates on, it's going to say, okay, the object is now the size that it is in our scene layout. In other words, if we stretched it out to be 5 meters now, if world coordinates is on, it's going to see the object as 5 meters. It sounds a little confusing, so let's take a look at some rendered examples. Might clear it up. Okay, here's our starting point. Our object is 1 meter square, and we're mapping on a brick pattern. This particular pattern has a texture size of 1 meter by 1 meter. In our scene layout, I'm going to go to the size gadget, and I'm going to size this box to be 2 meters by 2 meters. Okay, so here's the scene. We have a 1 meter object. We have a 1 meter pattern, our brick. Now we've gone in, we've stretched this object to 2 meters. But the image part of LightWave doesn't know this. It still thinks that our object is 1 meter because world coordinates has not been clicked on. So what do you think is going to happen? It's going to take that 1 meter image and stretch it to fit that 2 meter object. Now normally, if it knew that the object was 2 meters, a 1 meter image would fill it up. It would take 4 of them to fill up the 2 meter object. Do you follow me? But it doesn't know that the object is 2 meters across, so it's going to stretch it. Let's look at what happened when it was rendered. It stretched this brick pattern. The object is 2 meters across. The brick pattern should be 1 meter across, so it should take 4 of these brick patterns to fill it. But it doesn't know it's a 2 meter object, so it stretched the pattern to fill the whole thing. Now what we're going to do is we're going to click world coordinates on. Now it looks at the object and says, oh, it's a 2 meter object, and it'll adjust accordingly. If we look at our texture size, it's 1 meter by 1 meter in the X and Y axes. So it's going to take 4 brick patterns to fill up the object now instead of the 1, since it knows it's a 2 meter object. Let's look. Now this is what the pattern should look like. If we have a 2 meter object and a 1 meter pattern, this is what it's going to look like. It knows it's a 2 meter object now because world coordinates was turned on. Anytime you manipulate your object inside the scene, you're going to want to turn world coordinates on so LightWave understands how big your object is now. World coordinates will do a couple of things. It will tell LightWave how big your object is if it's been changed in the scene, and it will tell LightWave where your object is. Finally, let's take a look under texture, fall off, and velocity. In our scene, we have our ground, which we're going to map a cobblestone pattern onto, and our camera pointed directly at it. Under surface color, we go to texture. We see that we have a planar image map, and we're using the file cobble.iff. Under fall off, we've set 10 in the X and 10 in the Z. Now our object is 10 meters by 10 meters. We're going to fall off 10% every meter. So by the time we've come out to the edge, 10 meters, our pattern will have completely faded out, and it will return to the color set under surface color, in this case, gray. Let's take a look at the rendered picture. Here's our rendered scene. Remember, our object was 10 meters by 10 meters. We told to fall off 10% every meter. So by the time it hits the edges of our object, the pattern's completely gone. It fades to the surface color, which in this case was dark gray. Velocity is quite simple. Under surface color and texture, we go to velocity, and what we do here is we could set it to be, let's say, 10 in the X. That would move left to right 10 meters for every frame. Now that might be kind of fast. We could set it for 1/10 of a meter every frame, so that would take 10 frames to move the texture a meter. Now that would work with any texture you have mapped on your object. Let's use some of the techniques we've talked about so far in a useful application. This should be an especially useful lesson because we're going to learn to make the most out of simple objects. Modeling objects seems to be the toughest part of an animator's job, and it's certainly the most time-consuming. And for some, it's just too difficult to model complex objects. In this example, we'll make a simple object of a building, and we'll make that object look complex with some surface rendering techniques. Now, most of you should be able to model a building, even if you just do a box. We're going to learn how to make that box look like a complex building. Now that we're in Modeler, we're going to make a building. And now, like I said before, this is going to be a simple box. You can do this a couple of ways. One, by selecting the Objects box and drawing a box. That'll look a little bit like a building there, and hitting make. And that's all there is to it. Another way to do it is to hit the box icon, also hit numeric, this time entering coordinates under X box corner, start off at -25 and go to +25. Under Y, start off at 0 and go to 100. Under Z, start off at -25 and go to +25. Hit OK, make, then you can hit the A key to zoom out and see your whole building. If you like, you can go to Options and hit Static Preview and move around, and it's a simple box. Let's do one final piece of preparation work to it, and that is set its surface names. We'll need distinct surface names later when we assign materials to the object. To do this, we go under Surfaces, Edit. We'll need 3 names, namely Walls X, Create, Walls Z, Create, and Roof, and Create. We assign surfaces to the polygons by clicking on Polygon on the sidebar and highlighting each individual polygon by clicking on it. If we want to highlight multiple polygons, we can hold down the Shift key and click on the polygon. We have the X polygons, the X walls of our building highlighted. We're going to go to Surface, change Surface to, and we can scroll through till we find our Walls X and say OK. Click anywhere in the gray area on the side to remove the highlighted polygons, and now click on the Z-axis walls. Get rid of the X-axis this time and do the same thing. Go to Surface, change to Walls Z, OK. And we have one polygon left, that's the roof. So we click on it, click on the extra polygons to get rid of them. Surface, change to Roof, OK. Disk, and save our object. Let's look at the simplistic beauty of our object. First, there are very few points. Second, there are very few polygons. Now what this means is it's going to load quicker into LightWave, it's going to render a lot faster, and it's going to be easier to deal with. Now I know you're saying, David, that's great, but it still looks just like a box. Well, that's what the next part is going to be. We're going to turn that box into a complex object. Before we leave Modeler, though, I want to show you the object that we'll be using. It's a slight variation on the box. It's basically 3 boxes, one on another, with the addition of a simple flagpole, a roof, and sidewalks. There are thousands of variations that you can make from this simple box. Try using buildings in the city you live in, for an example. Notice that I still used very few number of points and polygons. Let's take a look at what this object will look like rendered out. Nothing fancy, but loads of possibilities. You see, the basic idea here is to model as few things as possible. Like the windows. You could go into Modeler and plot out each individual window, but when you finish, you'd have a huge object with 1,000 points that would take forever to render. There is a better, faster, and easier way. Let's go into Deluxe Paint. I'm in high-res 4-color mode. Now, 4-color makes for smaller, faster loading pictures. First, I'm going to need to set my palette. I'm going to need a black, a white, a dark gray, and a gold. Black will be the color used to show where windows are not. White will be the color used to show where windows are. Dark gray will be used to show windows where the lights are off. And gold will be used as the color of the windows. Now this color can be changed to any color you like, but leave black, white, and gray unchanged. First, I'm going to draw a large black rectangle. Next, I'm going to draw white windows using the brush in conjunction with the grid icon. I'll be able to paint down windows. Now using the brush tool, I will copy this over, and I will use dark gray in the fill command to turn off some of the lights in the building. When I'm finished, I'll grab my image as a brush and save it under the Images subdirectory of my toaster. Now to finish up, I'm going to grab a small box of the gold color and save it as a brush in my images subdirectory. That was easy enough. Do you see how much easier it is to design the windows in a paint program rather than modeling each one out separately? Getting back into LightWave, let's load our building. We also need to load our window pattern and our window color brushes, and in this case I'm loading a texture map called Granite for the concrete sidewalk. Now that we have all the pieces, I'm going to give you the theory behind all this. We're going to use the large brush of windows as a reflection map. We're going to use the smaller gold color brush as the image that gets reflected. Now wherever LightWave sees white, in this case the windows, it's going to reflect the gold color. Where it sees black, it's not going to reflect anything, and where it sees dark gray, it's going to barely reflect the gold, so it'll look like the lights are off. We need to adjust a few of the surface settings before we begin, such as the roof, making a dark red, the flagpole, a dark gray, and the separators between the parts of the building, a medium green. The concrete will be a texture map on the y-axis, being mapped straight down, not left to right and not front to back. The texture size will be x60 and z60 because that is the size of our building. And remember, since we're mapping in the y-axis, we don't need to adjust the y size. Finally, we pick the texture image we want, in this case granite. Now we get to the bottom of the building. On the X side, we go into reflection mapping and texture. We're going to select planar image map and our window brush, called Building Front 2 in this case, that we drew in Deluxe Paint. Under texture size, we put in our coordinates. Again, since we're mapping on X, we don't need to worry about the X size. But the Y size, up and down, was 75 meters. The Z size, front to back, was 50. Also, we need to set the texture center. In this case, 37.5 in the Y. Now let's look at how we got that 37.5. We're looking at the bottom of our building in the y-axis. It starts at 0 and goes up to 75 meters. The center of that is 37.5, so that is what we want the y to be set at, the center. Of course, these are just guidelines for you to use in your experimentation. And finally, we select the name of the image to reflect. Now we repeat this process for the bottom walls and the z-axis. When we're done there, we need to repeat the steps for the mid portion of the building and the top portion of the building. These are almost identical. I want to explain why. You may be tempted to enter a smaller texture image size for the mid portion of the building and the top portion, since they are smaller than the bottom portion. But if you do that, LightWave will compress the brush size to fit the smaller building size, and your windows will appear smaller, and that's not going to look right. You want the windows to be the same size, the top, mid, and the bottom portion. So keep the texture image size the same. Let's take a quick overview of our surface settings. For the bottom portion of the building where the windows are going to be, we've set a reflection map using the brush we did in Deluxe Paint. Under the texture portion of reflective map, we've selected the x-axis. Under texture image, we put in the name of the brush we saved under Deluxe Paint. Under texture size, we entered the size of our building. And under texture center, we entered in the center portion of our building, or the center coordinates. Under reflected image, we gave it the name of the gold color brush we saved under Deluxe Paint. We did the same settings for the Z coordinate portions of the building and for the mid and top portions of the building. When we render it out, it looks like this. Compare this to the previous picture. To change the look of the building, simply change the reflected image. Let's try clouds. If we like, we can set the reflective sliders for the roof and separators to 100%. set the reflected image to the same cloud pattern, and get this glass-looking building. By using a little creative camera positioning, we can get striking effects. And it all started with a simple model. Let's try it again with another very simple building. This one is made up mostly of a cylinder. Notice this time, when I created the cylinder, I had double-sided polygons turned on. When we render out our untouched model, it looks like this. Now this time we're going to reflective map our image using cylindrical image mapping. Now this time we're going to reflective map our image using cylindrical image map. Remember when we used planar image map, if we mapped on the z-axis, we didn't need to enter a texture size value for z? In cylindrical mapping, it's just the opposite. We're going to map in the y-axis, but this time, under texture size, we only need to give it a y size. It assumes that it's going to wrap the image one time around. It just wants to know how high. In this case, our building was 120 meters high. As an example, look at this bottle of creamer and imagine the label is our image. LightWave will automatically adjust the X and Z to wrap it one time around our cylinder. We only need to tell it how high in meters the image needs to be. We now have to center our image. This time, this is how we'll figure out where the center of the image belongs. The base of our building is 40 meters high. The tower portion where we're doing the map is 120 meters high. We divide the tower portion in two and add that to the base of 40 and get 100 meters. So under Y, we enter 100. When we render our object now, we get windows. But wait, we want these windows to be transparent. Under transparency, we can apply the same map. Under texture, we go under cylindrical image map, assign it the same picture building front, the y-axis, make sure the texture size is the same, and your texture centering is the exact same as before. Now remember, wherever LightWave sees white, it's going to make things transparent. Where it sees black, it won't affect it at all. If there were gray, it would be a medium transparency. This time when we render, transparent windows. Do you see the other side of the building inside? That's there because our image was two-sided when we made it in Modeler. Again, by using a close-up camera view, we get striking results. And it all started with a simple cylinder image. Try these techniques with some nighttime scenes. Since the windows are reflections, they look good in any light. And remember, experiment and use your imagination. We use buildings here because they make good examples. But our main purpose was to understand some of the features of LightWave. These same techniques for reflective and transparency mapping can be used in hundreds of different ways. Thank you for joining us on our second edition of Helpful LightWave Hints. We hope you enjoyed it, and more importantly, we hope you've learned something that'll help you in your rendering and your LightWave animations. If you have any suggestions on how we can improve, please call us and get in contact with us. If you have any LightWave successes you want to share, or if you have any problems, feel free to give us a call and we'll try and help you out. Until next time. The Video Toaster set new standards in performance and price in the desktop video production arena. The Personal SFC by Nucleus Electronics does the same thing for single-frame controllers. Now, to take full advantage of LightWave, you really need to use a single-frame controller and tape deck. Now, previously, these could cost anywhere from $1,500 to $3,500, and that doesn't even include the price of the deck. However, the SFC by Nucleus costs only $425. Included in the price of the package, a cable for connecting your Amiga serial port to your tape deck, a simple-to-understand manual, and one disc containing the software. For this demonstration of the personal single-frame controller, we'll be using our standard Amiga 2000 with the personal single-frame controller software already installed. Our video deck is a Panasonic 7750. This is the one with the built-in time-based corrector. Retails for about $6,500. We also have an optional timecode generator board inserted, which sells for about $500. Now, this timecode board generator is optional for the Panasonic, but it's not optional for the single frame controller. It is required. So that's our equipment. Now let's look at how we actually run the software. Installation of the single frame controller couldn't be easier. One end goes into the serial port on the back of your Amiga, and the other end goes into the remote 9-pin port on the back of the VTR. Installation is quick and easy. Upon booting the SFC, we come to the configuration editor, which gives us settings for frame correction and pre-roll time, among other things. When we say OK there, we're presented with the main menu, which looks a lot like a VTR. Buttons for play, record, pause, and other VTR functions are included. On the right side, we're presented with a number of animation options. We're going to go to Anim for this demonstration. Upon entering the animation sequence editor, we are told how many frames that we can do in memory. 2000 is fine for us. We'll hit OK. We are then asked under timecode for drop or non-drop frame. For our demonstration, we use non-drop. Then we're asked for the starting time on the tape. Clicking last directory and image name will ask us what type of sequence we're going to send for recording. For this example, of course, we'll use toaster render. Then it asks us for the number of frames in our toaster render. For this example, we'll hit 30. It then gives us an edit decision list for 30 toaster frames. Under count, we can set how many frames will be recorded on tape for each frame the toaster renders. If we put in 2, it'll universally record 2 frames every time the toaster outputs a frame. We'll set it back to 1. At the first frame, though, we'll enter 30, and on the last frame, we'll also enter 30. This will render 1 full second for the first image and last image. When we're through, we go to record. Once we select Automatic Render, LightWave begins drawing frames. The SFC takes control of our VTR, automatically pre-rolls, and waits at the appropriate frame. Upon completion of each frame, the VTR rolls up and snaps into record long enough to record the frame. The process is repeated until the animation is complete. Terry Smallwood and the group at Nucleus Electronics have come up with a real winner in the area of single-frame controlling. I highly recommend that you look into it. Technical support is good, installation of the software is easy, and operating the software is also easy.